All right, guys. So this set of notes is covering the first part of Unit 4, which is biochemistry. So what biochemistry is it's the study of the chemistry or the chemicals, the elements, the compounds that come together to make life or biology happen. So to first start, we need to have a little bit of a background in what chemistry is and kind of the pieces of chemistry. um Everything in our known world, in our known universe, is made up of atoms, and a collection of these atoms is called an element. So we're made of elements, and how they come together kind of determines the properties of whatever that may be. So what an element is, it's a pure substance, and it's just one substance. So an example of this could be like gold. If you find pure gold, or if it's pure gold that's been melted down and separated, then that would be made up of the element called gold. Aluminum foil is just aluminum. There's nothing else in with it. So elements cannot be broken down any further. That's as far as they go in terms of making the atoms. And they are going to be represented by one or two letter symbols. So a couple of examples. C is for carbon. So anytime you see the big letter C, it means carbon. H is for hydrogen. Sodium is Na, and mercury is Hg. And that comes from those two elements, their Latin name, which I don't remember what their Latin name is off the top of my head, but that's why sometimes they get a little weird. A compound is when you take two or more elements and then you chemically put them together. It's a chemical combination. So a compound means that the atoms that make up that element have to connect with each other. So I can't take some aluminum foil and shred it up and then mix it in a bowl with gold and call that a compound. They would have to be chemically combined with one another to make one uniform thing to be considered a compound. Parts of an atom. So, like I said, an element is made up of atoms of all one kind. And the atom is made up of kind of three different parts. You have these subatomic particles. There are two of them in the middle of the atom, and conveniently enough, this middle, this kind of like head honcho of the atom, is called the nucleus. So we've heard that term before. But the two particles that are found in the nucleus, these are your protons, which are positive, and neutrons, which are neutral. So be very careful with that. It is something that students will sometimes mix up with the neutrons. They think neutron negative, but just remember neutron neutral. It's not positive, it's not negative. Just like if your car is in neutral, it's not going forward, it's not going backward, it's just staying there. Electrons, these guys kind of go all over they surround, or they orbit the nucleus very quickly. And they can kind of go anywhere within this cloud that surrounds the nucleus, but the electrons are the ones that are negative. And for the most part, for a neutral overall atom, the number of electrons will be equal to the number of protons, because you want the atom to be without a charge, an overall charge. So what an atom looks like, again, here in the middle, this is our nucleus. You have the neutrons and the protons. Protons have the positive charge. Neutrons don't have anything. You can also see these represented sometimes by a 0. And then your electrons orbit around the nucleus. So they don't get to come into the nucleus. They just kind of stay at a distance. And so how the electrons behave, that's going to indicate how that atom is able to connect or combine with other atoms. The periodic table of elements, this was put together, I believe, in the 1700s by a scientist. His last name was Mendeleev. And Mendeleev, he kind of started putting things together just like a puzzle. They started discovering these atoms, and how he did that at that long ago, I have no idea. But he started putting them together, and at the time, there was known information about protons, but nothing about electrons or neutrons really at the time. So he started kind of just playing around with like cards that had the information that was known about these elements. and he started to put them together in a pattern. And so his work that he did 300, 400 years ago, whenever it was, really paved the way for the periodic table of elements, which is just a really nice way for chemists to put the atoms, or excuse me, the elements together, to kind of show their properties. And there's, again, it's just a really nice like pattern, and it's a really nice visual to be able to use to determine the characteristics of a certain element. So, all right, so when we look at our on the periodic table of elements, each element has its own little box or its own little card, and that part of the table tells all that you need to know about the element to be able to predict what type of reaction it would have or how it would respond with different elements. So when we look at our element identifiers, the first thing that we look at is the atomic number. The atomic number in this element card or this element properties, the atomic number is the number of protons. It's also the number of electrons, because we are assuming that these elements are neutral, that they don't have any charge at all to them. So the atomic number is the same as the protons. It is the same as the neutrons. All right, the big letter that's in the middle, we call that the symbol. It's like the abbreviation for the element, and then the name is underneath. The atomic mass is typically found in the upper right-hand corner. They can also be found, if we look here, right underneath the atomic symbol. But how you can kind of distinguish between the two, or excuse me, between the atomic number and the atomic mass. The atomic mass for most of the elements will have a decimal, because just like with anything, the mass or the weight can fluctuate kind of depending on the situation. Um, these elements down here that don't have a decimal, that's for a kind of different reason that we can talk about in class. But anytime that you see a decimal or you see brackets around the number, that's going to mean it's the atomic mass. So sometimes it's sometimes shown in the upper right hand corner, but it can also go right underneath the symbol and the name, in between the symbol and the name. But the atomic mass is going to be the number of protons plus the number of neutrons. And so because those neutrons have no charge, you can have as many neutrons as you want, and it'll change the atomic mass, but it will not change the atomic number, because that atomic number is based on the number of protons. So to calculate your atomic mass, protons plus neutrons, in this case, if our carbon always has 6 protons, does not matter how many neutrons it has, carbon will always have 6 protons because it's atomic number 6. And then if in this particular element or this particular sample we're looking at, the carbon atom has 6 neutrons, that means that the atomic mass would be, let me turn this on here. So if we have 6 protons, and we know that has to be true because our atomic number is 6, plus in this particular example, this particular element we're looking at has 6 neutrons as well. That means that the atomic mass would be 12, and then we characterize it by AMUs, that's the unit that we use. So if I'm asking you to find the number of neutrons, you would just go and work the opposite direction. So we know that the atomic mass is 12 minus 6. It has to be 6 again because of that atomic number. So that means that we would have 6 neutrons. And you can do the same thing for multiple elements. And typically the problem will show something along the lines of lithium, which is atomic number 3, excuse me, has 4 neutrons. What is the atomic mass? So if that were the case, lithium always has 3 protons. I'm telling you that in this particular example, there's 4 neutrons. That means that 3 plus 4 equals 7. So in this example for lithium, the atomic mass would be 7 AMUs. So that is kind of the process behind finding these characteristics and being able to solve them mathematically. We're going to do this practice in class, so you can leave this portion of your notes blank. We're going to do this in class together, so don't worry about it too much right now. All right, the electron shell, as mentioned earlier, the electrons are the thing that makes it so that the element will behave in a certain way. So the electron shell follows, for the most part, this thing that's called the octet rule, meaning that in order for the shell to be happy, it has to have 8 electrons. Now, the exception to that rule is the first orbital. Because it's so small and it's so close to the nucleus, it can only fit 2 electrons on it before it's considered quote unquote happy. Okay. Um, so for sodium, there are 11 total electrons that we would be working with for a neutral atom. And so what happens here is we put the first 2 of 11 on our first shell. So now we have 9 remaining to work with. Well, 8 of them, let me go ahead and mark these up here. So we put 1 and 2 on that first shell because it can only fit 2. So 11 minus 2, we now have 9 electrons remaining. So we can fit 8 on the second orbital. So here's numbers 3, 4, 5, 6, 7, 8, 9, and 10. So we had the first 2 on the first orbital, 3 through 10 go on that second orbital, and then we have 1 remaining on the third orbital. Now, sodium really doesn't like having this one lone electron on its outermost shell. It hates that. Actually, it makes it very volatile. But if we look over here at chlorine, chlorine on the outermost shell has 7 electrons. So having that one extra electron, taking it away from sodium, would make chlorine really happy, and it would make sodium happy because it would be losing that electron that it really doesn't vibe with. And so that's how we're going to make chemical reactions happen. So again, just kind of talking about the octet rule, when the outermost energy level is full, that's when it is happiest. So in order to do that, and this is that same picture that's from the last slide. So in order to make the octet rule happen and to make the atom happy, the element can either donate electrons, so it can say, hey, I'm not using this, you can have it. And then the other element will accept those electrons. So it'll be like, hey, thanks, man. And the other option is they can share the electrons. Like, hey, I need this one, but I see you have a blank space. Like, let's go ahead and share it with each other. So that in this right here, the satisfying of the octet rule, this is what creates atomic bonding. So an isotope, if we take a look at our picture up here, we have carbon, and then we have carbon-13, and we have carbon-14. So the difference between these 3 carbon, they're all carbon, so that means they all have to have 6 protons because they're considered carbon. They have to have 6 protons. The thing that changes between them is the number of neutrons. So in carbon, normal carbon, what we typically work with, or we can also call this carbon-12, there are 6 neutrons, and then 6 plus 6, 6 protons plus 6 neutrons will give us the atomic mass of 12. In carbon-13, we still have 6 protons because it's carbon, but now we have 7 neutrons. So 6 plus 7 equals 13. So the atomic mass of carbon-13 is 13 because it has an extra neutron. In carbon-14, the atomic mass is 14. Well, we know that of that atomic mass, 6 of the mass units come from protons. So that means in carbon-14, you have 8 neutrons. So isotopes means it's the same element. The thing that changes is the number of neutrons. And because of this, the atomic mass will change. And on top of that, once that happens, the nucleus will also be bigger because it has to house more stuff. And so isotopes can also react slightly different with one another, or with different elements. All right. Compound. So what a compound is, this is when chemical combination happens between 2 or more elements. This again will happen through what's called chemical bonding. And the rules with this is that it's that octet rule. The elements really want to be happy. They want to have a full outer shell. So In this case, again, for sodium, sodium has that one lone electron. Chlorine needs that electron. So instead of having this weird, unhappy electron on the outermost shell of sodium, it'll just go ahead and give it to chlorine. And now the outermost shell of sodium with electrons on it is full, it's happy. And the outermost electron shell of chlorine is also happy. So everybody wins. A free radical, this is going to be a molecule with one or more unpaired electrons in the outermost shell. So this would be our free radical from sodium. Free radicals inside an organism can lead to diseases. And so how we can combat these free radicals is we can consume antioxidants. The antioxidants, because they are using elements that are not oxygen, typically our free radicals inside the body are oxygen. The antioxidants will match up with those oxygens that are not full outer shells, and it will make it'll make that oxygen less volatile. All right, so that's where we are going to pause for this ed puzzle. We'll continue discussing in class, and we'll start working with bonding. If you have any questions, please let me know. Otherwise, I will see you in class.